Here's the multiple choice questions from the gas summative assessment. Questions 1, 2, 3 gave us 4 different gases. At 273 Kelvin, they are at the same temperature. They are in 4 identical rigid containers, which must mean plastic, metal, glass, and all the same volume. Question 1 says, which of the following is true of the gases listed in the table above? They're in reference to average kinetic energy, which is measured by temperature. So as long as the gases are at the same temperature, they have the same average kinetic energy. Now that may not translate into the same speed. Speed will depend on the mass of the particles, but average kinetic energy is temperature. Number 2, the best explanation for the slightly lower pressure in container D is that the SO2 molecules end up being polar. So ignoring container B, A, C, and D all have approximately 1 atmosphere of pressure, but yeah, D is a little bit less than I would expect. A and C are both nonpolar, as well as gas B, which we'll talk about in a second. Nonpolar gases versus gas D, which is polar. Now you might have to draw the dot structure, check your electron count. This can be drawn 2 ways, and we'd have to use formal charge to say which is best. But it should be bent either way. There would be a lone pair on that central sulfur. So because gas D, the SO2, is polar, the intermolecular forces may be a little bit stronger depending on the volume of the container and all that good stuff. So because there may be stronger intermolecular forces, the gas particles are a little more attracted to each other, so they may be colliding with a little bit less force or frequency, and the pressure is less. Now, number 3, the gas with the greatest density. Okay, so they're all in the same container, so we can assume that they're at the same volume, density being a measure of mass per volume, grams per liter. So same volume, but we want to know then like which container has the most mass. They do give me the molar masses of these gases, and that's right, like sulfur dioxide is about 64, carbon disulfide 76, the carbon dioxide's 44, the O2 is about 32. So the most common wrong answer is C. Now, if we know that these gases are in the same container at the same temperature and pressure, they would have the same number of particles, which maybe would end up being a mole. But wait a second, if the gases were at the same temperature and pressure, they would have the same number of particles in the same container. But gas B has double the pressure. So how do I get double the pressure in the same volume container at the same temperature? There must have been double the moles. So instead of there being 1 mole, there must have been 2 moles. Or instead of 44 grams, 88 grams of gas, which then beats C, the carbon disulfide, at 76. So that's kind of the trick with number 3. How do we get double the pressure? There must be double the moles of gas. Number 4, a balloon is filled with 0.25 moles of helium at 273 Kelvin in 1 atmosphere. It is allowed to rise through the atmosphere. Which of the following explains what happens to the volume of the balloon as it rises from ground level to an altitude where the air temperature is cooler, 240 Kelvin, but the pressure is much less? And so we've got like kind of conflicting data here. The temperature is going down, which if the temperature is going down, they're asking how the volume would change, and I'd say, well, then the volume should go down. Temperature and volume are directly proportional. But then on the flip side, I'm lowering the pressure, and under lower pressure, the gas would expand to a higher volume. So these seem to be kind of conflicting until I really kind of look more closely at the data. The temperature is decreasing, but in Kelvin, it's not that dramatic. And all gas variables are proportional to temperature in Kelvin. But my pressure is decreasing by a factor of 10. So a 10-fold decrease in pressure is going to have more of an impact on the volume than a slightly lower temperature. So we'd expect the volume of the balloon to increase because the decrease in air pressure will have a greater effect than the decrease in temperature. Number 5, I have a mole of butane and 6.5 moles of oxygen mixed in a closed container fitted with a movable piston as shown below. The mixture is sparked and allowed to react as completely as possible according to this combustion equation. Which of the following is true after the product gas is returned to the original temperature and pressure? And why will the change occur? Okay, so we're going to do a little combustion. I do notice that I've got 1 mole of butane and 6.5 moles of oxygen, which is the stoichiometric ratio, comparable to a ratio of 2 to 13 moles. So I'm going to completely react both the butane and the oxygen. There'd be no limiting, no excess. So the only gases present in the container after the reaction occurs should be the carbon dioxide and water. Now we're going to return to the original temperature and pressure, so those factors aren't going to apply here. But if I look at the balanced equation, I start with 15 moles of total gas and I form 18 moles. Or I could look at the ratio of what I do have. I have, 6.5 plus 1, 7.5 total moles. And so I could then say, okay, I would form, 9 total moles of product. But the key is that pressure and volume depend on the number of particles, not necessarily the identity of the particles. So if I'm going to form more gas than what I started with, the piston should be at a higher position than original because now we contain more gas particles. Not unchanged like in B or C, and not lower because the molecules are maybe smaller. I mean, I guess the butane is a pretty big molecule, but pressure really just depends on number of collisions, volume, number of collisions, number of particles. A is the best choice here. More particles should give me a greater volume inside that container. Number 6, we've got a graph that shows the distribution of speeds in a sample of hydrogen at 50 degrees Celsius. Which of the following shows the distribution of speeds for a sample of hydrogen at 25 degrees? So same gas, but at a lower temperature. So at a lower temperature, those gas particles should just be moving at a lower average speed. So maybe something like gas D. Seven and 8 are looking at exceptions to the ideal gas law. Ideally, gases aren't supposed to have significant intermolecular forces. They're far apart, they're always moving, but carbon tetrachloride deviates more from ideal gas behavior than CH4. And it must be that the London dispersion forces are just a little bit stronger. There's more total electrons, it's more polarizable. So if I did have stronger dispersion forces, there's a chance that those particles would be more attracted to each other and maybe they wouldn't collide as frequently or as forcefully as I would expect. Both nonpolar gases, so we're really just dealing with London dispersion forces. Number 8, I've got 2 samples of helium in identical containers at the same temperature, which would deviate most from ideal behavior. And so again, particles aren't supposed to interact with each other, but if I do anything to put them close to each other, now there's a greater chance that those intermolecular forces could come into play. So one option would be just to use more gas. If sample 1 has more total gas particles, they'd be a little closer to each other, and that would give me a greater chance of potential intermolecular forces. Number 9, I like this one. You just have to think about this one a little bit. The figure above represents 3 sealed 1-liter vessels, each containing a different inert gas at 298 Kelvin. Inert just means non-reactive, so they're all noble gases at the same temperature. The pressure of the argon in the first vessel is 2 atmospheres. The ratio of the numbers of argon, neon, and helium are 2:1:6 respectively. There are 4 particles, 2 particles, and 12 particles. After all the gases are combined in a previously evacuated 2-liter vessel, what's the total pressure? Okay, so we're going to mix these 3 gases in a 2-liter container at the same temperature. And so we know then that if I add gases, the pressure is just the total pressure from each individual gas. But then I have to figure out the total pressure from each individual gas. Now that'll just be dependent on the number of particles. So if I notice that the argon has 4 particles and that pressure is 2 atmospheres, if there's only 2 atoms of neon in the same container at the same temperature, the pressure should be half. So I could say then that the neon would be 1 atmosphere. If there's 12 atoms of helium, that's triple the amount of particles of argon, so it should be triple the pressure. I should have 6 atmospheres of helium. Now I'm going to add all those gases together, which you would maybe think 9 atmospheres, and of course that's one of the choices. But we're putting those gases in a larger container. So if we put them all in a 1-liter vessel, then yes, the pressure would be 9. But if I double the volume, the pressure will go down by half. So now the total pressure should be 4.5. I like that one. That's a thinker, right? And the last one, number 10. We've got some butane again, C4H10, placed in a rigid vessel with a movable piston. The volume of the gas is reduced by moving the piston downward while the temperature remains constant. The pressure of the gas versus its volume is plotted on the graph below. We kind of did this in the lab. We pushed down on the gas, and we could see that at my highest pressures, I've got my smallest volumes. Which of the following best explains the increase in pressure of the C4H10 butane when the volume is decreased? The best choice is A. So it's a closed container. I've got the same number of particles, but I'm squeezing those particles into a smaller space. There's just going to be more collisions in that smaller space. The particles will collide more frequently. Now, sometimes people will put C, that they collide with greater force, and that might be applicable if the temperature were also changing, that then the particles would have more kinetic energy and they're moving around faster, they collide more frequently and more forcefully. But here the temperature is the same. So the best explanation is probably A, that we're just forcing all those particles to collide in a smaller space. So in that smaller volume, they'd be colliding more frequently.